Hi, this is Mrs. Vrobel. This is part one of covalent bonding. So, in the previous unit, we talked about ionic bonding, and now we're going to talk about the difference between ionic bonding and covalent bonding, and how do you identify a covalent bond. So, before we do that, I want to show you a simulation here. So, with this simulation, we have two atoms, and notice that one of them has low electronegativity. Now remember, when we're talking about electronegativity, we're talking about the ability for the atom to hold on to its electrons. So if you have high electronegativity, it holds on to its electrons very tightly. If it's low electronegativity, it releases its electrons more readily. What I'm going to do here is I'm going to show you the bond character. Now, with a dipole, this arrow shows us that the electrons that reside between A and B are actually pointed in this direction. And if I click on the density, you can see where this is less electron density, here's greater. So I'm going to increase the amount of electronegativity. And look at how it's mostly gray on the left-hand side, and it's mostly white on the left-hand side, and then it's primarily gray on the right-hand side. Also, notice the bond character. So we went from, let me show you again, we went from somewhere in between ionic and covalent to mostly ionic. So notice how when you have an extreme difference between electronegativities, you're looking at ionic bonding. Now, let's reduce it down to less. Notice that if both of the two atoms have similar electronegativity, it's considered mostly covalent. And there's no white. It's essentially just a plain gray color between the two atoms. Let's see what happens with 3. So here we have 3 different atoms. I'm going to change the electronegativity on C. So when I do, notice how the dipole, or where we have the electron density, changes, and it's more in between the B and C atoms. Now let's go to a real molecule. So here we have hydrogen and fluorine. I'm going to show the molecular dipole. So this yellow arrow tells me where do we see most of the electron density. And notice that there's a little white here, and then it's mostly gray, almost black. Now I'm going to show you the electronegativities at the bottom here. So here we have fluorine, it's 2.1, and fluorine is 4.0. So hydrogen differs significantly from fluorine. Now just for comparison, let's try hydrogen. So here we have 2 hydrogen atoms, and notice that there's no molecular dipole. And that's because both of them are sharing equally. If you look at electron density, it's all gray. So they're sharing their electrons very nicely. Okay, let me do one more. Let's look at fluoromethane. Okay, so fluoromethane, there is a molecular dipole, and it's pointed in fluorine's favor. We have 3 atoms. We have hydrogen, chlorine, and fluorine. And notice that hydrogen is slightly smaller than carbon. Fluorine still has the strongest electronegativity. And when you look at electron density, notice that it's lighter color towards the bottom of the molecule, and it's darker color towards the top. Now, how does this relate to covalent bonding? So let's look at covalent bonding. So when we're talking about covalent bonding, we're talking about 2 nuclei that have same attractive force on a pair of electrons. And the nice thing about covalent bonding is they actually share their electrons. And remember, the electrons are negatively charged, and there's 2 nuclei on either side of those pair of electrons. Now, I don't know if you remember, but we talked about quantum mechanical structures, and we talked about the s orbital. And the s orbital is the shape of a sphere. So we have 2 overlapping spheres that form this covalent bond. And notice that with this overlapping of these two spheres, we get what we call a covalent bond. Okay, chemists like to get more detailed about what they're talking about, and when we are talking about a covalent bond, we're essentially talking about, oops, sorry, trying to get my pen going here. Okay, there's an interesting symbol here. It's called a sigma bond. So SIG, for those of you that don't know Greek, sigma bond is essentially you have two electrons and they're right in the middle of two positive nuclei. Now you could have another type of bond where it's instead of S orbitals, we could have a PP orbital. So remember those balloons, those lobes, they can overlap and they could form a single bond. So we could have something like this. So with a p orbital, we essentially have two lobes overlapping, and there's two electrons that reside in that overlapping. We also can have a perpendicular set of p orbitals that are overlapping. Now this is specifically called the pi bond. So you know the symbol that you've seen, 3.14. Okay, this is called pi bond. And you need to have p orbitals in order for this to happen. Okay, and this is actually found in multiple bonding. So you're going to have more than just a single bond. And then a third type of bond that we could have is what we call an S and P. So we could have a sphere with a p orbital overlapping, and that essentially creates a covalent bond. Okay, now there actually are situations where we can have polar covalent bond. Now before I do that, I just want to show you. This is an electronegativity chart. So notice that wherever you see like that dark fuchsia, that's where the electronegativity is the greatest. And then if it's more of a faded white or gray color, that's lower electronegativity. Now, when you look at the periodic table, notice that like hydrogen is darker in color. And obviously this section in here where a lot of the non-metals reside, that is very dark in color. You do have a slight group of electronegative atoms in the transition metals, but we're actually more concerned with this section and hydrogen. Now let's go back to what is a polar covalent bond. Okay, so what happens is there are some atoms that don't play nice, and they actually kind of hold on to their electrons more than usual. So we call it unequal sharing. Now with this unequal sharing, what happens is you essentially have a partial charge, and this partial charge has an interesting symbol to it. Okay, this is called delta. So this is a delta charge, and if it's a partial positive, you'll see a delta positive. If it's a partial negative, you'll see a delta negative. So if a molecule which has a covalent bond has unequal sharing of electrons, we call it having a dipole. Okay, so as I mentioned before, this is a very similar chart that I just showed you. The only difference is it's blue instead of fuchsia. And it is helpful in deciding whether or not you have an electronegative atom. But, I would just notice that if you are talking about atoms that are close together, their electronegativity is not going to be as great. But if they're more than one space apart, we're talking about a greater separation of electronegativity. Okay, here we go. So these are the different types of single bonds that we can see within a covalent bond. So we can have essentially an S-S overlap. So when we have an S-S overlap, we have a covalent bond there. And notice it has the sigma symbol to it. So these three are sigma bonds. We could also have two pp lobes overlapping. And when they do, they create a single sigma bond. Or we could have the instance where we have an S and a P orbital that overlap, and together they form a sigma bond. Okay, this is the last segment of this video. So what we need to do here is identify the polar covalent bond. And I'm going to do the first three, and then you'll do the last two yourself. So here I have hydrogen and fluorine. Now, if you're not sure whether or not this is polar covalent, and I'll tell you, I threw in some ionic bonds here, so you have to be careful, okay? Let's go to the periodic table first, just to find out what's going on here. Okay, so here we have hydrogen, and we have fluorine. So would you say that the electronegativity difference is high between the two of them? If you answered yes, you are correct. So looking at this problem, is this a polar covalent bond? I would say yes. Okay, and that's because H's electronegativity is lower than fluorine. So there's enough of a difference between the two. All right, so the question is with chlorine, is chlorine a polar covalent bond? Well, let's go back to the periodic table. Okay, notice that chlorine is all the way over here. Okay, yes, it's very electronegative. Now, let's go back to our problem. Okay, is it polar? No, it is not polar, because when you have two atoms that have the same electronegativity, they're going to share their electrons. Remember that example we saw in the beginning with hydrogen? Hydrogen bonded to itself, it's sharing its electrons equally, so it is not polar covalent. It is covalent, but not polar. Okay, here's the last one. We have sodium chloride. So let's go to the periodic table and take a look at that. Okay, so here's sodium. It's light in color, and here's chlorine. It's darker in color. It's not as dark as fluorine, but it's definitely darker than sodium. So the question is this polar covalent? So looking at this molecule, is it polar covalent? No. Why is it not polar covalent? Sorry, my N looks terrible. It's ionic. So whenever you have a metal bonded to a non-metal, it is not covalent. Okay, that's where the little clue is. Look to see if there's a metal in there. If there is a metal in there, it's not going to be covalent. It's going to be ionic. Okay, so you're going to do the last two on your own, and they'll be part of the video assessment.